Okay, in the previous class, we have discussed the concept of circular convolution. Okay, so we have derived an equation where ym is equal to summation of x of n, x1 of n into x2 of m minus n modulo n from 0 to n minus 1. Okay, where m is from 0 to n minus 1. This is what we have called as circular convolution. In place of ym we have written here x3m. Okay, now we'll see how you can find the circular convolution of two signals. Again, the process is same. You have to keep one signal as it is, you have to fold other signal, then shift it, then multiply, and then add. The equation is very much similar to the linear convolution. The only thing is that the folding and the shifting is to be done in a circular way. Okay, so I take say simple example. Suppose you have x1n is equal to 1 2 3 4, one sequence, and another sequence here, suppose 2 1 1 2. You have to find the circular convolution of x1 with x2. Okay, so first thing that we do, we represent these sequences on a circle now in a circular way. This is x1n, and the second sequence you have x2n. So this is x10, this will be x1 of 1, this point is x1 of 2, and this point is x1 of 3. So it is 1 in this case, 1 2 3 and 4. Similarly, this is x2 of 0, that is 2, then it is 1, then 1, and it is 2. So what we do now, we again fold one sequence, then multiply with another sequence, add, you will get y0, the first sample. From this equation, if you see y0, it is nothing but x of 1n, x2 of minus n mod n, because m is 0. So x2 of minus n mod n is nothing but the folding of x2. So I fold this sequence, x2 of n. I will get x2 of minus n mod n, the folded sequence. So folding of this means you have to simply write this. Initially we have written this sequence in the counterclockwise direction. Now if you fold it, you have to simply write in the reverse direction. It means it will be 2, then 1, then 1 and 2. And then you have to find the product, x1 into x2 of minus n mod n. So you have to multiply these two signals together. When you multiply these two signals together, you will get the product, that is x of 1 of n into x2 of minus n mod n, and in this case is 4. So how you multiply this? When you multiply it, this will be multiplied with this sample, so 2 into 1, it will become 2. Then this sample is multiplied with this, 2 into 2 will get 4. Similarly, 3 with 1, 3 into 1, 3. This is 4, this is 1, 4 into 1, 4. This is the product sequence, and then you have to finally add all the samples together. So this is how you get y0. So it is 2 plus 4 plus 3 plus 4. Okay, what is it? It is 13. Okay, similarly you can get y1. Now when you calculate y1 from this equation, it will be summation of x1n x2 of 1 minus n modulo n. Now 1 minus n is nothing but the first fold, then shift by 1. Okay, so this is already folded sequence. If I shift this by 1, I will get x2 of 1 minus n mod n. Okay, so you have to now shift it. You shift it, what you will get, so this is 2 1 1 2. If you shift it by 1, so what sequence you are going to get? It will be shifted by 1 unit in this direction, so you'll get 1 2 2 and 1. Okay, this is shifted by 1 in the counterclockwise direction. If it is 1 minus n, if it is minus 1 minus n, it will be shifted to the reverse direction. Again, you have to multiply this sequence with the x1 n, multiply and add. So if you multiply it, you'll get 1 into 1. So 1 plus 2 into 2 will get 4, plus 3 into 2 6, plus 4 into 1 4. Similarly, you can get y2, you can get y3. Okay, you can compute this. Now you have to shift it by 2, this sequence, then by 3. Okay, now when you shift it by 4, 1 2 3 4, it will again become the same sequence. It will repeat basically up to 4. Okay, so you'll just get the 4 unique samples: y0, y1, y2, y3. y4 will be same as y0. Okay, this is how you find the circular convolution of two signals. You can complete this answer, you can find the rest two values. Okay, now what is the utility of this circular convolution? Because see, when in time you see, when we have seen the filters, the linear systems or linear filters, you have seen the concept of filtering, that if you pass a sequence xn through a system having impulse response hn, your yn is the linear convolution of xn and hn. It is not the circular convolution. Okay, or you can say that y omega is equal to x omega into h omega. So how you can use DFT in linear filtering? In that case, what you should try to do, it means if I find the circular convolution of the two signals, if that somehow becomes equal to the linear convolution, in that case I can use DFT for linear filtering. Okay, in C I have a sequence xn, I am passing it through a system with impulse response hn, and yn is the linear convolution. If somehow I try to manipulate so that yn is not the linear but the circular convolution also of xn and hn, or you can say that the circular convolution of xn and hn becomes equal, in that case whether you multiply the Fourier transforms or their DFT, the output is going to be the same, isn't it? Right now what we have x omega into h omega, and the inverse Fourier transform of this, that is IDFT. If you compute, you get a sequence yn which is the linear convolution of xn and hn. On the other hand, if I take its DFT, I multiply them and then I take IDFT, this is IDTFT, sorry, I get a sequence yn which is equal to the circular convolution of xn and hn. Okay, Now if I want to use DFT for linear filtering, it means if you multiply the two DFTs, if I take its DFT xk, then I take its DFT hk, I multiply them together and I find the output yk, and then its inverse yn, that should be the same as the linear convolution. If it is same as the linear convolution, actually it is circular convolution, but we have to make it equal to the linear convolution, then only we can use it for filtering. Because in the linear filters, the output is the linear convolution of x and h, not the circular convolution. Okay, but in the DFTs, if you multiply the two DFTs in the frequency domain, in the time it is the circular convolution. So how you can do that? What you can do in this case is that your input xn has some length, suppose L, and the impulse response of the filter has a length, suppose M. Okay, so what is the length of output? Since output is the linear convolution of the two signals, it is L plus M minus 1, and I write it as suppose N. Now when you take the DFTs, initially what we have done is we take L point DFT here, then we take M point DFT here. But if I take its M N point DFT for both cases, it means my Y omega is equal to X omega into H omega. It is already there, this equation. If I take N point DFT of this, and that is equal to N point DFT of this multiplied with the N point DFT of this. Okay, it means you are taking M samples. Okay, the Y omega, which is the product of X omega and H omega, in the DFT domain I take its, because see its length is N is M plus N minus. Suppose this sequence has a length of 3, this has a length of 4. What is the length of output? It is 4 plus 3 minus 1, 6. Okay, it means to represent in the DFT domain, the number of samples must be greater than the length of the signal. So for Y I must take minimum 6 samples. For X I can take 3 samples, for H I can take 4 samples. But in this product, if I take the 6 samples of Y omega, okay, so that will be same as if I take the 6 samples of X omega multiplied with the 6 samples of H omega. Okay, it means if I take the N point DFT of X, that is xk, and N point DFT of H, that is hk, I multiply them together and I find the inverse DFT. In that case, my output will have a length which is equal to the length of linear convolution. Okay, this is how you can use the circular convolution for computing the linear convolution. Okay, it means you have 3-point sequence, you have 4-point sequence. Okay, the length of linear will be 6 point. Now to find the linear convolution using the DFT, what you do, you take the 6-point DFT of X, 6-point DFT of H, multiply them together, find the inverse DFT, you will get the circular convolution. Okay, just I will take one example. Suppose I take a sequence xn, which is a 4-point sequence. Suppose 1, 2, 3 and 4, and then I take another sequence, maybe the impulse response, which is 1, 2, 1, suppose 1. Okay, the question is that this xn is applied to a system having impulse response hn is equal to this. You have to find the output yn using DFT and IDFT maybe. Okay, Since it is a linear time invariant system, so you know that yn will be the linear convolution of xn with hn. So if I am using DFT and IDFT to find the response of the system, what I have to do? If I just take its 4-point DFT, that is xk, and 4-point DFT of h, that is hk. If I multiply them together, xk into hk, and I find it inverse discrete Fourier transform, what will be my output? This will give the circular convolution, or not the linear convolution. It means this is not my output. But if I take the output, the DFT, because it is a linear convolution, so what is the length of output? This has a length of 4, this has a length of 4, so 4 plus 4 minus 1 is 7. It means if I take the 7-point DFT of this, the 7-point DFT of this, multiply them together, find the inverse DFT, I will get the linear convolution. Okay, and generally we avoid to compute the 7-point DFT, so we go for the 8-point DFT. So since this sequence has a length of 4 samples, to compute its 8-point DFT, we have to use 0 padding. So I have to add 4 zeros to this, and similarly to HN, I have to add 4 zeros, 1, 2, 1, 1, 0, 0, and 0. Okay. Now find the 8-point DFT of this, then 8-point DFT of this, multiply them together, find IDFT, you will get yn, which is the linear convolution. Okay, this is how you can make linear convolution equivalent to circular convolution, or you can say how you can find the linear convolution of two signals using the circular convolution. Okay, I can verify 1 or 2 samples, rest you can do. Suppose I find the linear convolution of these two signals, sorry, circular convolution, and that will be equal to the linear convolution of these two signals. If you find the linear convolution of these two signals, it is 1, 2, 3, 4, 1, 2, 1, 1. So it is 1, 2, 3, 4, 2, 4, 6, 8, then again 1, 2, 3, 4, 1, 2, 3, 4. So you have to add them together. The linear convolution of these is 1, then 2 plus 2, 4, 4 plus 3 plus 1, 8, and so on. We are getting 7 samples. Okay, now what I am saying is that I can get the linear convolution using the circular convolution if you use 0 padding. If you pad xn with 4 zeros and hn with 4 zeros and find the linear circular convolution of x and hn, that will be same as their linear convolution. Okay, and how you do that? I have to first plot x. Since it is circular, I have to plot x of n and h of n on a circle. So 8 points you have, 0, 1, 2, 3, 4, 5, 6, and 7. So it is 1, 2, 3, 4, rest 4 points are zeros. Similarly in the h of n, this is 1, 2, 1, 1, sorry 1, 2, 1, 1, 0, 0, 0, and 0. Now you find the first sample using the circular convolution. You have to fold one sequence. Suppose I fold it. If I fold this sequence, it will become, I have to write in the reverse direction, so it will become 1, 2, 1, 1, then 0, 0, 0, and 0. Then you have to multiply with the another sequence and add them together. So your y of 0 will be equal to 1 multiplied with 1, 1 plus Next, these samples up to here, they are zeros, and from this to this, these samples are zeros here. So that's product is 0. So y0 is 1 plus 0 plus 0. You are getting 1. So first sample is Sam. Okay. Let's start verify one more sample. If I find y1, y1 means now after folding we have to shift it by 1 units. So if I shift this signal, folded signal by 1 in the counterclockwise direction, what I will get? 1 will become go here. This is 2, then 1, then 1. Rest are zeros. Now if you multiply these two sequences, so it is 2, it is 1. So 2 into 1, 2, and 1 into 2, 2. So 2 plus 2 is 4. Rest are zeros. So y1 will be equal to 4. Similarly, you can find y2, you can find y3. You will get all the samples of the linear convolution. Now since the length of output is 8, sorry, the length of output is 7, but you are computing a 8-point circular convolution. So automatically what you will get 7 non-zero samples in this circular convolution. The last sample y7 will be automatically 0, because there are only 7 samples in the linear convolution. In the circular convolution, although you will get 8 samples, but the last sample will be 0. Okay, so generally we compute 2-point circular convolution or 4-point or 8-point or 16-point, because these points are easy to place on the circle. Otherwise you can calculate 6-point also, no issue. Okay, but we prefer if the signal has a length of suppose 5 samples and you have to find its DFT or circular convolution, so we generally prefer to go for the higher powers of 2. That is, for 5 length we will calculate 8-point DFT or 8-point circular convolution. Okay, so you have to complete this question. You have to find all the samples. I have just calculated 2 samples. You have to find y2, y3 up to y7, and you have to show that the circular convolution is the same as equal to the linear convolution. So by zero padding the circular convolution of the two signals, that becomes equal to the linear convolution, and that is how you can use DFT for linear filtering. Okay, it means if you pad both the signals, the input signal and the impulse response, with zeros, so that the length of the signals becomes equal to the length of the output. In that case, if you multiply the two DFTs and find the IDFT, that will be same as the linear convolution, or you can just say the circular and the linear convolution, they will become equal in that case. Okay,